So polarity is a partial positive or negative charge at the end, or one of the many ends, of a molecule. So stuff like hydrogen bonding, where, oh, we have a hydrogen that's bonded to, say, oxygen or nitrogen or some other electronegative atom, and that hydrogen ends up partially positive, and thus it binds to, say, another oxygen on another molecule, so say water. That is partially negative. Well, that relies on polarity. It relies on dipoles. What are dipoles? Guys, if we have one end of the molecule being generally positive, well, somewhat positive, and the other end being somewhat negative, we have two poles, a positive pole and a negative pole, thus dipole. Now, since these dipoles can occur in many different places on one particle, or one big molecule, like say a big protein, hydrogen bonding we considered a subset of dipole bonding, and dipole bonding, well, that's pretty much, partial positives and partial negatives. It's not necessarily that the whole molecule has to have poles. So here, for carbon dioxide, we have the carbon being partially positive and both oxygens being partially negative. But carbon dioxide is nonpolar. Why? Because, hey, electrons are pulled towards this side. Electrons are also pulled towards that side. So tug of war, and overall it's symmetric, nothing happens. It's symmetric, and very importantly, there isn't enough space in the middle for, say, another partial negative to insert in, and hey, both the neighboring parts are partial positive. Great. No, that doesn't happen with carbon dioxide. And for oxygen, well, they're the same element. They have the same electronegativity. So, with diatomic oxygen, it is nonpolar because they both pull at the electrons equally. They have a delta En of 0. So delta En, difference in electronegativity of between 0.5 and 1.7, is considered polar. Here we see methanol and water molecule. We should note that even though the carbon with lots of hydrogens attached is considered to be nonpolar, if we attach this hydrophilic, so water-loving group that can hydrogen bond with water, we can freely solubilize, so we can make miscible, some pretty sizable hydrocarbon chains. I mean, propanol is miscible with water. It can mix in any ratio. And so can, for that matter, tert-butanol. Now, for propanol, technically we have isopropanol and N-propanol. So in other words, hey guys, if we mark methanol as this, so that implies that there's a CH3 over here, by the way. So if we mark this as just this structure, ethanol, which is the alcohol that is drinkable without going blind, unlike methanol, it would be this structure. And propanol, or 1-propanol, technically, although you still see lots of bottles labeled as N-propanol, would be this thing. And then there's, not enough space, isopropanol, which would be also 3 carbons, but the OH comes out in the middle. And then for tert-butanol, We're talking this stuff. For just one hydroxyl group to solubilize this thing? Yeah, that's big. Why? Oh, hey guys, oxygen has molecular mass of, well, this hydroxyl group has molecular mass of 17. Oxygen has atomic mass 16. And, well, carbon, even not counting those hydrogens, we're looking at 48. And counting the hydrogens, we add another 9. 57. Okay, this thing is quite big for only one hydroxyl to solubilize. So as we can see, hydrogen bonds are very strong. How can we see this? Well, if this is miscible, i.e. mixable in any proportion with water, it must be able to bind quite strongly with water. Okay, intermolecular forces. Well, intermolecular forces are between molecules, much as international is between nations. Interpersonal is between people. Okay, van der Waals forces are very weak. I mean, we have the stronger ones. We have ionic, being second only to covalent. Covalent is the strongest because they share electrons. Ionic is next. And then we have, well, hydrogen bonding, or dipole-dipole in general. And finally, we have van der Waals forces. Now, van der Waals is also known as London dispersion. And it's a matter of, hey, the electrons just happen to randomly be more on this side of the molecule. Okay, the other side becomes partially positive, this side becomes partially negative, and what happens to the next molecule over? Well, that reacts to this end being partially negative, and its electrons move over. So the end that's nearer becomes partially positive for a brief moment, and the partial negative and partial positive attract one another until the partial negative disperses for whatever reason. So this is very weak attraction, but it's van der Waals forces that enable a gecko with its fine hairs on its feet to manage to have enough contact area close enough to, say, walls or even glass to climb straight up of glass panels or walls or hang upside down on ceilings. Geckos are a type of small lizard that you may or may not be familiar with. You are welcome to look them up. Hydrogen bonds, well, we mentioned this, and here, wait a second, what do you think happens when this solidifies? So instead of transient hydrogen bonds with water molecules slipping past one another, by the way, they are transient, but they are also strong enough that you can hold up a paper clip on the surface of water. Because, well, the high surface tension is due to a matter of, guys, there's nothing over there, so above the surface, to hydrogen bond with. So they hydrogen bond very tightly to one another instead. And thus we have the very high surface tension. Now, what do you think happens when this freezes? Well, the hydrogen bonds enable the establishment of a crystal lattice, which gives water the unique property of being less dense as a solid than it is as a liquid. So ice floats. This is very important for life on Earth, because otherwise ice would just sink to the bottom of oceans and only the top layers would thaw out when it's warm enough to do so. And given the fact that having really shallow water, it means more reflected light than deep open water, a lot of Earth would remain frozen, essentially permanently. All right. Here we have some nonpolar molecules, and we can show London dispersion forces, like say on methane. Now these forces, also known as van der Waals forces, are really, really weak. So it's only when you have some really, really long molecules, big molecules don't necessarily work. Because if you take these atoms and configure them into the most branched thing you can so that it's like a ball, that's not much area to come into contact with one another and thus have van der Waals forces. You need long chains so that, okay, not only do we have van der Waals forces from proximity, but we can also potentially tangle together. That's why stuff like, say, hexane, due to van der Waals forces, can remain liquid at a much higher temperature than methane. Octane can remain liquid at room temperature. And, well, tar, which has many more carbons, well, that's a very viscous liquid at room temperature. It doesn't flow readily. Now, part of that is because the molecules are just so long that they can tangle together. Part of that is due to van der Waals forces. Polar molecules also have van der Waals forces between their positively and negatively charged regions. But it's just that the van der Waals forces are usually used to refer to random biases and random attraction, not the sort of systematic thing you have in polar molecules, where it's very steadily, oh hey, the chlorine is going to be partially negative and the hydrogen is going to be partially positive. That's considered generally dipole-dipole. Okay, some common chemical reactions that we deal with in biology include dehydration reactions, where what happens when we want to take two molecules that have hydroxyl groups or carboxylic acid and alcohol, so hydroxyl and carboxyl, and we want to make them into one bigger thing. Well, we get rid of the water, and lo and behold, they are now welded together by covalent bonds to the same oxygen. So this is also called a condensation reaction. So why do we call this condensation? Well, what is condensation? Well, usually we use that as, hey, we cool a gas mixture down, water vapor condenses and becomes liquid water, and leaves the mixture. I wonder what this water could possibly be doing relative to the molecules. Well, obviously it's leaving the molecules, right? Hence why they decided to, oh, let's call this a condensation reaction. Condensation reactions are different from condensation, even though sometimes we abbreviate. Okay? Now, hydrolysis. We know that hydro is water and lysis is to break apart. So hydrolysis is to use water to break something apart. Now, no, this is not, oh, let's take this high pressure water stream and use it to cut something. Yeah, no. In this case, we're adding water to a bond and we're breaking it apart. So it's a reverse process of dehydration reactions. Now, some other reactions we might have to deal with for biology are neutralization reactions, where acids and bases combine and create a salt and water. So salt is a general term for ionic compound. Whether or not this salt is solubilized in the water that's also produced, or whether it comes out as a precipitate, will vary depending on what we're dealing with. So redox reactions, well, they're electron transfers in the sense of, hey, one molecule gets oxidized. It undergoes oxidation. And the other molecule is reduced or undergoes reduction. Oxidation, why is oxidation the process where electrons are lost? Aren't, well, say, oxygen molecules or oxygen atoms really good at grabbing electrons? Well, hey, guys, we know that rust is iron oxide, okay? So we know that oxygen is everywhere in the atmosphere, and, well, okay, mostly everywhere. It is really good at grabbing electrons. We know that fluorine's better, but it's expensive and hard to isolate compared to oxygen. So let's use oxygen as a general term. And we see these oxides forming everywhere. So let's use that almost as a verb. Okay, oxidation. Hooray. Yeah, that's pretty much more or less the general gist of how the story came about, of calling oxidation the process of having electrons taken away. Let's use oxygen on this, as opposed to, behaves like oxygen. So reduction is a process where a molecule gains electrons. Now, we should point out that the molecule that gets oxidized is a reductant. And the thing that gets reduced is the oxidant. The oxidant oxidizes the other thing. It itself gets reduced. The reductant reduces the other thing. It gets oxidized. Okay, in summary, isotopes are different forms of the same element. They have different numbers of neutrons, and, well, they generally, chemically speaking, because chemistry is for the most part a matter of the electrons, they generally have fairly similar chemical properties. Yes, okay, there are some differences. For example, heavy water is different from normal water, especially in utility in, say, nuclear reactors. And they do have some differences in physical properties. And yes, okay, photosynthesis does have isotopic bias, and that's why you can tell when an athlete's hormones, as sampled by urine samples, are from soybean-produced hormones and injected, or whether it's their own body producing it. Okay, true, but chemically they mostly act similarly, very similarly. A radioisotope is unstable and decays to release particles. Now, a radioisotope may have too many protons, or it might have too many neutrons, so the decay routes will differ, depending on the isotope in question. And even then, a particular isotope may have several different possible decay pathways. Alright, valence electrons are the electrons in the outermost electron shell of an atom. There are 4 types of chemical bonds in biochemistry: ionic, covalent, hydrogen bonds, or dipole bonds, and van der Waals forces / London dispersion forces. Names may vary. Electronegativity is a measure of an atom's attraction for electrons, and differences in electronegativity result in bond polarity. So, fluorine is rated at 4.0. Hydrogen is rated at 2.2. Hydrogen is rated at 2.2. Oxygen is at 3.5. Chlorine is at 3.0. So it might be interesting, hey, wait a second. We know that hydrogen chloride dissociates really readily in water. Why? Well, the chloride anion is very stable, which helps promote dissociation, even though it's not nearly as ionic of a bond as, say, hydrogen fluoride. Hydrogen fluoride is actually a weak acid compared to hydrogen chloride. So hydrofluoric acid is considered a weak acid, even though it can etch glass, unlike hydrochloric acid. Why? It's because the fluoride ion is a little bit small for the charge it carries, which means that it's not as stable as, say, chloride is. Okay, Intermolecular forces are attractive forces between molecules. Just like international is between nations and interpersonal is between people. Dehydration is the removal of hydroxyl and hydrogen from two reactant molecules. Now the other end generally also has a hydroxyl, but sometimes you have stuff like, say, an amine instead. And this end could be, say, a carboxyl. Where does that happen? Well, in peptide bonding, we have amino acids reacting to form peptide bonds, which are amide bonds. Now that's also dehydration, but it's not an ester or an ether. So we form a single larger molecule and water. So hydrolysis occurs when a bond in a large molecule is broken and water is added to the resulting subunits. So water is added to break the bond, more specifically. Oxidation is electron loss, reduction is electron gain. That's because oxygen is really good at grabbing electrons off of other things, so to have something become oxidized, like say treat it with oxygen, is a matter of, hey, let's grab some electrons off of it. So the oxidation of one particle is always linked to the reduction of another, because, well, the electrons don't just vanish into nowhere. This is called a redox reaction. You could argue that, say, oh, hey, I take a battery and I make the electrons go from the battery into the wire. Guys, if you have a wire that's connected to, say, a lamp, or even just to the other end of the battery, which would be short-circuiting it, and a matter of using the wire as a heater, because the electrons have to dump all their energy, all their potential energy. Hey, if you do that, the electrons still end up going in the other end of the battery. And then you'll have coupled your oxidation reduction reactions. So, well, oxidation and reduction half reactions, which are a concept we cover in chemistry class instead. Well, this overall is called a redox reaction. So oxidation reduction reaction. Ox-red. That doesn't sound so nice or formal. Let's call it redox instead. And no, it's not red ox. Okay, so that's it for this section. This is some of the fundamental chemistry that we must know for biology purposes. So we'll see each other again then, next section.